All right, thank you for this introduction. Hopefully all of you will understand more about what I'm presenting about here. When I walked up the stairs here, I know that there's this quote from Albert Einstein saying logic will get you from point A to B, but imagination will get you everywhere. I started thinking about it because I don't know if this holds for fuzzy logic as well, which will be part of my discussion today. Who of you is familiar with fuzzy logic? Okay, if I ask this question again in 30 minutes from now, hopefully more people will raise their hand. That's part of my my talk, not the main focus. Yeah, so I will present a package for topic modeling using fuzzy logic, fuzzy clustering. So my name is Emil Rijcken. I'm doing my PhD at Eindhoven University of Technology, and I'm positioned in Den Bosch at the Hieronymus Academy of Data Science, also called HIATS. The consortium I'm in is called COVIDA. And although the name almost resembles COVID, it doesn't have to do anything with it. It stands for Computing Visits Data. Yeah, just the name of the project. It's a collaboration between Eindhoven, the UMC Utrecht, Universiteit Utrecht, and the Leiden University Medical Center. We work in mental health care and natural language processing in mental health care. So yeah, again, I will present FuzzyTM, a Python package for state-of-the-art fuzzy topic modeling. A few big statements. The first in the world for fuzzy topic modeling. We also have user-friendly pipelines, and in the meantime, also modular design allows for other algorithms to be added. I'll discuss this further during the talk. Yeah, so then you understand better why. So is everyone here familiar with topic modeling? Okay, that's good. For the people that aren't, I still will introduce it a little bit. The official definition, I think, or the one I often use in my papers is that it's an unsupervised natural language processing algorithm that extracts latent topics in text. And there are many different algorithms out there for fuzzy topic modeling. But what most of them have in common is that you input a corpus, which is a document of, or a set of documents with text, and you need to set the number of topics that you want to find in your algorithm. And then typically the algorithm returns two matrices. One is the probability of a word given a topic, and the second one is the probability of a topic given a document. And then for the way most people use this algorithm is that from the first matrix, they take the top n words per topic, and those, if the algorithms work the way we want them to work, follow some kind of theme or topic. So here's a example. Oh wait, yes, sorry. So we have this matrix. Suppose we train our corpus on a data set with lyrics, and we want to find 3 topics. Then, ta-da! Here you see 3 topics and 10 words per topic. Can anyone see which lyrics this is about? Well, that's irrelevant, but so this is the idea of topic modeling, that you get words, and then if they follow some kind of distribution, you recognize themes in them. And then you can use those topic models either just to analyze documents, but you can also use it as to create embeddings of other documents and use this input for text classification. That was actually the motivation why we started working with topic modeling. So probably most people that know topic modeling know LDA, latent Dirichlet allocation. However, there are many different algorithms out there. Yeah, so Prot LDA is also one of the newer ones, works with neural networks and LDA. LSA is an older one, latent semantic analysis. I think it produces, or it performs singular value decomposition on a document term matrix, and then returns the U and the V matrix as both matrices that I just mentioned. So if there are so many algorithms out there, why should we care about fuzzy topic modeling? And since I saw little hands in the beginning, what does fuzzy mean? What is fuzzy logic? To illustrate the idea of fuzzy logic, I have the following picture here. And who thinks this is a black dog? Who thinks it's a brown dog? Okay, I see some hands, but there's some doubt. This directly illustrates the idea of fuzzy logic, namely that in this case a duck can have a membership to certain sets. Here it has some membership to the set of black ducks and some membership to the set of brown ducks. And that is the opposite to crisp logic, where you just have one definite set. For this reason, I think if you have fuzzy logic, it won't just bring you from point A to point B, but maybe partly membership to point C or B, whatever. To illustrate this further, you have a line and your membership. Here you see the membership degree to set of black ducks. Well, the white duck, the white puppy, and the bottom left doesn't have any membership to this set, and the blacker the ducks get, the higher their membership. And you can use this logic to model various phenomena. So if you compare probabilities with fuzziness, probability is the relatedness to randomness, and uncertainty described by the tendency or frequency of a random variable to take on a value in a specific region. And fuzzy sets are related to gradualness. I think you all already have a intuition of what it is, but the next example will even clarify this more clearly. So please all close your eyes and imagine yourself walking in the desert, and unfortunately you've lost your water. It's a really hot desert, and you're thirsty, and all you can see is desert and sand. And after having passed so many sand dunes, you hope to see something else than desert only. So now you're walking over the next sand dune, and the first thing you see is this. You can open your eyes now, and you become really happy. But the reason why you're so happy is not because you see her. No, there's water. So there are two bottles. You're really thirsty, so you want to drink. And then you see the labels on those bottles. And one says there's poison in this, or the membership to poison of the first bottle is 0.10. And the other one says the probability of poison is 0.1, also 0.10. Now you're thinking, like, which bottle should I drink? You know that you can safely drink water with a membership of poison of 15. So the membership of 10 is lower than 15, so you can still safely drink it. However, the one with the probability of 0.10 gives you a 10% chance that the poison is so high that you can't drink it anymore. That's the clear intuition of what fuzzy logic does and what memberships mean and how they compare to probabilities. Which bottle? Who will go for the membership? What is it? I think everyone will give the same answer. Okay, so that's fuzzy logic. And why then should we care about fuzzy topic modeling? So our reasoning is that probabilistic topic models estimate the probability of finding a word in a topic. However, we think it's more intuitive to think that words belong to topics with some kind of membership. And hence we started working with fuzzy topic modeling. So what is it? Last year we proposed a new algorithm. There was already an algorithm called fuzzy latent semantic analysis, which is based on LSA. And then we proposed a alternative to it. We called it FLSA-W, which stands for FLSA words. And we found really good results. So this is the idea of the pipeline of the algorithm. You start with your corpus. Then for your corpus you create a document term matrix. So it has all the different vocabulary words as rows, and each document is a column. You just count the appearance of words in documents. Then based on this matrix you calculate global term weights, which could be TF-IDF, which I think most of you will be familiar with, but you can also choose entropy, for example. And then, it goes too fast. Based on the global term weights, you use singular value decomposition for dimensionality reduction. So actually until now this is LSA. But then with FLSA and FLSA-W we go further. We take I always confuse if it's the U matrix or the V matrix, but one of the matrices from singular value decomposition with the characteristic that it has the number of words by the number of singular values. We cluster in this space, and then using Bayes' theorem and matrix multiplications, we find the right matrices. that will return the outputs as all algorithms do. If you want to see how we did it, there's a reference to the paper. So we ran results to see how our algorithm compares to other algorithms. So what you see on the left is a few of the algorithms we built compared to other algorithms. We also tried a different approach, which we called FLSA V. It's harder to run and it didn't perform as well. So here I focus only on FLSA W. I think we ran it on the M10 dataset. We ran it on various open datasets, so it can be verified. In each column you see the number of topics. So what we did for each number of topics, we ran each algorithm 10 times, and then we reported the average performance metrics. Often topic models are evaluated using the coherence score, which indicates how well words within a topic support each other. And with support each other we mean how often they co-occur in your corpus. But that only focuses on the quality within a topic, and this is a little bit limited, because if you have one topic with words that all support each other, then the coherence would still be high if you had 3 identical topics, which doesn't make sense so much, we think. So there's also the diversity score, and that looks at how different topics relate to each other, and if they are all unique, or to what extent, to what membership, no, they have similar words or different words. And then the interpretability score is just the product of the coherence score and the diversity. Here I'm just proudly showing our results compared to other algorithms. If you want, we ran this on various data sets, also DBLP, BBC News, and the 20 News Group. This link shows you all the experimental results. So that's another motivation for using fuzzy topic models. Also recently we've developed FLSA E. We try to fill all the letters in the alphabet, so we still have a few letters to go. This one stands for FLSA embedding. So here we train a word-to-vec embedding cluster, then in this embedding space, and perform matrix multiplications to also find the right output matrices. Also this work has been published. I presented it a few months ago in Prague. The coherence score of this model is good, however the diversity is pretty low, so we still need to look into this further to see how we can make it work better, because we suspect that this in the end will be a better approach. It is featured in FuzzyTM. So we have 4 different algorithms featured currently in FuzzyTM. The original algorithm FLSA, then FLSA W, FLSA V, and FLSA E. Currently we have a new idea which I call FLSA C, but it's not featured here yet and not published. As you can see, the algorithms all go through a similar set of steps to find the output matrices, and that's also how the package works. So here you see one mother class, FuzzyTM, and then for each algorithm there's a child class. I don't think even people in the first row can see what it says. So here, these are the most important methods in the package. So when you run an algorithm, you just initialize it as FLSA or FLSA W. You need to give your corpus and the number of topics, and then when your model is initialized, you just run the method get matrices, and that then connects to the mother class, goes through the steps as indicated in the algorithm, and then returns the output matrices. So since we're at PyData, insights into the code itself. When you run this algorithm, you need to input a list of strings or of tokens, and we have a hard check in the beginning to make sure that this is the right data that you input, so no issues occur later on. So since in the beginning of the algorithm we work with a document term matrix, which is the number of the vocabulary size by the number of documents. Your data set could be, or data frame could become really big. For example, we worked with the hospital data and we had 90,000 unique words and maybe 4,500 documents. So that's, I think, a space of like 300 million cells. And that's you can't really handle that. So therefore we use sparse matrices, in this case the doc matrix, which is a dictionary of keys. You can use it with SciPy, I believe. Yeah, you can still use arithmetic operations with it, and it's just an efficient way of handling your sparse data. Yeah, we use PyFume for fuzzy clustering. It's produced by one of my other peer PhDs and my same promoter. But if you want to use clustering, it features FCM, which is an alternative to k-means clustering. It's just a fuzzy alternative. So if you want to use fuzzy or clustering in general, I also recommend using this Python package to see what your results will be like. Also, their paper is published at IEEE, FuzzyIEEE. Yeah, so another method in our Python package is the getTopic embedding. So you can use topic modeling to analyze text on its own, but you can also use it to embed your documents for other downstream tasks. So with the method getTopic embedding, you can input new documents, and then it calculates the extent to which different topics appear in your new documents, and then you can use those matrices as input embeddings. There are different settings here that you can play with, and we haven't experimented with the results of what the best methods are. So you can set the top n words that you want to use to represent your topic, but also percentile of top words that you want to include, and then it just looks in the text to find these words and calculates the percentage, I guess, to the extent of which they appear. Yeah, so there's also just this save in the load method. If you have trained your fuzzy topic model, since it uses fuzzy clustering, which is randomly initialized in the beginning, and you want it will return. It's not deterministic, so it will always return different results. So therefore, the save and load method will help you to save your method and work on it later on. We use Pickle to save models. Oh yeah, so in the beginning, one of the claims I made about FuzzyTM is that it has user-friendly pipelines, and it can be ran with 3 lines of code. Looking at this code, you might be counting and be like, hey, there are more than 3 lines. But those are the only lines needed to train it. So you, yeah, in the beginning we just used the Octis data as an example, M10, for which I also showed the experimental results. So after you have installed FuzzyTM, you import FLSAW. Then you initialize your model saying FLSAW, and then use your data and set the number of topics. And then you just run it to get your output matrices. So you get your first one, the probability of a word given a topic, and the probability of a topic given a document. And then once your model has trained, which is pretty fast compared to other algorithms, you can see your topics using the FLSA show topics method. If you use representation as words, you'll see the words only. If you use representation as both, then you will see both the probabilities or the memberships and the words. To get the scores, the performance scores, you just use get coherence score, get diversity score, or get interpretability score. For coherence, it typically needs to work a little bit or think a little bit to write the fine code or the right score, just because it looks at the corpus and the co-occurrence of the words in your topic. So this will be the output of our model, the coherence score of 0.53, which is relatively high compared to other algorithms. The diversity score and interpretability score. So the dependencies of FuzzyTM are NumPy, Panda, SciPy, and PyFume. This used to be sparse SVD as well, but there were some troubles to install this, so we got it out. Yeah, just a short wrap up of what I discussed. So we've developed the first Python package for fuzzy topic modeling. Our algorithms outperform other state-of-the-art algorithms. A model can be trained with minimal effort, and users can plug in their own methods. To quickly go back and give an example. So I told you that I'm now working with FLSA C. We got this idea last Monday. Wait. So I discussed last Monday with my promoter. Oh, maybe we can do this and this step to get new output matrices, and then it only took me 20 minutes to implement it using the package, just because all the modules are there already, which was nice. Okay, yeah. So right now we're also working on an extension for FuzzyTM for topic analysis. So typically only the coherence score and diversity are used to evaluate a topic. However, I find this weird because it's a set of sets. It's like you try to summarize all this multidimensional data with one value or two values only. So in this extension, we will use different methods to analyze your topic, more like a descriptive statistics of your topic models to understand them better. Also we've pushed our repository to GenSim, so there will be an implementation there as well. I suppose you're all familiar with GenSim since you know new topic modeling. And if anyone has ideas for other algorithms that work in some kind of similar pipeline, then please push it to the repository. We will look at it, and this way we can extend the package as well. Here are my contact details, so you can find FuzzyTM on my GitHub. Also, every now and then I write blogs about topic modeling, but also other subjects related to NLP or data science, which you can find on my Medium account, Emil Rijcken. This is the end of my presentation. I can't see how much time is left, but thank you. Are there any questions? Several questions. Ladies first.
Really great presentation, really interesting. Thank you a lot. I was just wondering, so the only input you provide is the corpus, right?
Mm-hmm.
So it determines the topic itself.
So the question is, the only thing that you provide is the corpus, and yes, that's correct.
And then could you perhaps provide a few examples of applications of this that you could imagine?
Okay, so I'm repeating all the questions, so it's recorded. So if I can mention some applications using topic modeling. So for example, what we used it for as well, one of our students worked with feedback data in the hospital. So people that have gone, had a surgery at the hospital, then later they were asked what they liked about their help and what they didn't like, or the care. And this is a lot like a big data set with many written comments, and it's hard to analyze it. Using topic models, we find the topics that many people focus on, and this way it can be used to analyze it. So it's often used for seeing what kind of support or what kind of feedback is given, what people talk about if you have large data sets. And the motivation for us to use topic modeling is to make text classification more interpretable. So typically when you work with text classification, you have your input embedding, like a BERT embedding or word2vec. You feed this into your algorithm. It can be any kind of classification algorithm, and then you have your output data. But then even if your model works well, it's hard to see how your classification algorithm made its decisions, just because the high dimensionality of your word embeddings. The idea with topic modeling is that for each input dimension, you know what it stands for because it's some kind of topic. And then if you feed that to your classification algorithm, you see the weights to each topic, and in this way it could make text classification more interpretable. Those are two examples. Okay. Another question in the back.
Yeah, so thanks for the presentation. I really liked it. How do you find a good way to determine the number of topics before?
Good question. So the question is, how do you determine the number of topics beforehand? It could be done with trial and error. Some people use the coherence score to find some kind of optimal coherence score. I'm not a big fan of this. It kind of depends, I think, on the level of specificity of what topics you want to see. Currently, I'm also looking at kind of the specificity of words produced by a topic. For many algorithms, it holds that if you increase the number of topics, they become more specific. So they contain words that appear less often in your corpus than when you use less topics. So it kind of depends on your desired results, what kind of context you want to see your topics to be in to set the number of topics. And it's as with many things in data science, I think the answer is also just go and try and see which number of topics give the best topics. Okay. Another question?
Yeah, and you have exactly 5 minutes left.
Okay.
I wondered if you can say anything about the coherence score that you're using and the diversity score, because there is no such thing as the single coherence.
Good. Okay, thank you. So the question is, I shouldn't stand in front of this, if I can elaborate on the coherence score that I use and the diversity score, because there's no such thing. Because there's several coherence scores indeed. This coherence score I mentioned here is the CV coherence score. Simply the reason we use it, there's a paper from 2015 by Röder, and he compares many different types of settings of coherence scores and finds that the CV correlates most with, or highest with human interpretation. So that's what we use here. We use the Jensen implementation in the package, so you can use all kind of CV scores to get your coherence score, but the default will be CV. As far as the diversity score, I'm not sure if there are different definitions.
I know some people use the reverse blue score, for example, to measure diversity.
Oh, okay.
You might have used something different.
Yes, exactly. Okay. Interesting. I would like to hear more about this. Well, so the formula for the diversity score is the number of unique words in all your topics divided by the total number of words. So if each topic has unique words, then the score will be 1. But if different topics share some words, then the score will be lower. It's always a score between 0 and 1. It can be 0, but a little bit more. Okay. Any other question?
You also discussed the method used like word effect, right?
Mm-hmm.
There are also a lot of like language models, like words, you also mentioned it, that are also used for top modeling purposes. Are you also planning to experiment with that, or?
Oh yeah, thanks. So the question is, in FLSAE we work with word-to-vec, word embeddings, but there are also now more state-of-the-art embeddings such as BERT, contextualized models to work with. And yes, I'm planning to work with that as well. There are some BERT models already, topic BERT I believe, and CTM I think. But yeah, I will look into that as well. Okay. Any other question? No? Okay, well thanks for your attendance, for being here, and enjoy your day here at PyData.